All right, so this next paper I'm going to read is called High Dimensional One-Way Quantum Processing Implemented on a D-Level Cluster States. It's a Nature Physics letter and by a bunch of people, collaboration. What led me to this paper was Lucia Caspani. I listened to her presentation at Clio this past May, and I wanted to learn more about these cluster states on chip. And I found this paper that was highly cited. I mean, it's a Nature paper, so obviously. And I wanted to just see if I could understand it a bit more. And let's see where Lucia or Lucia. I think she's from Cambridge, I think. She was 9. Institute of Photonics, Department of Physics. Oh, Glasgow, UK. There's people from all over. Quebec, Canada, Cambridge, the USA one, Italy, Canada again, China again, Australia, UK, like I said, Japan, another UK, but a different university, China, and Russia. So, pretty much all over. This Christian Remmer, where is he from? He's the first one. He's from Quebec, Canada, Institut National de la Recherche Scientifique. Christian. He's also at 2 in Harvard University. So I'm gonna look him up. Sorry, I'll get into it, but I'm on this trail now for some reason. Okay, so this is the main author. I think usually in physics, the main author will be put at the front. Yeah, it looks like this Michael Hughes and Roberto Morandati. They have, I think they must, Remmer and Hughes. I'm guessing Remmer and Hughes are related somehow. There it is. Yeah, so they kind of, I think they're this, I think Hughes and Morandati, I think they are kind of the main people of the group. I think that's how it usually is in physics, where the people who did the most of the work are in the front. No, I don't know. Let's see. Is he postdoc? What is he? Hyperlight Corp. I don't know. So I don't think he's postdoc. Just going to open the window one sec. All right, I think this is pointless, so all right, let's read it. Okay, taking advantage of quantum mechanics for executing computational tasks faster than classical computers, or performing measurements with precision exceeding the classical limit, requires the generation of specific, large, and complex quantum states. In this context, cluster states are particularly interesting because they can enable the realization of universal quantum computers by means of a one-way scheme. So I've heard of that before. That's where you have a cluster state, and when you measure it, measure out all the modes of the cluster state in a certain pattern that corresponds to a quantum computation. And if you have a three-dimensional cluster state, that computation is universal. And it's a one-way scheme because once the cluster state has been measured and you've done the computation, you cannot go back and you have to generate the cluster state again. So the analogy is like drawing a circuit, drawing a quantum circuit in the sand, and then the water washes over the drawing and erases it. Whereas in the analogy, the water is the measurement. Where processing is performed through measurements. The generation of cluster states based on subsystems that have more than 2 dimensions, D-level cluster states. So, for example, a qubit is a superposition, let's say, of a horizontally and vertically polarized photon. That's a 2-level or 2-state system. But if there's more than right, based on subsystems that have more than 2 dimensions, right? So you can have subsystems of, say, 5 photons. That would be a 5-level cluster state. Is that what they're saying? Based on subsystems that have more than 2 dimensions, whatever. Provides increased quantum resources while keeping the number of parties constant. And also enables novel algorithms. Here, we experimentally realize, characterize, and test the noise sensitivity of 3-level, 4-partite cluster states formed by 2 photons in the time and frequency domain. What does 3-level, 4-partite mean? I will figure it out. What do I think it means? D-level. What is a D-level cluster state? I'm not sure what D-level means. Subsystems that have more than 2 dimensions. So maybe that's like a 3-dimensional. Yes, three-dimensional cluster state. Maybe I'm thinking maybe that's a 3-dimensional cluster state with 4 partites. So there's 4 photons. So I think it's a 3-dimensional cluster state with 4 photons. Confirming genuine multipartite entanglement with higher noise robustness compared to conventional 2-level cluster states. I think 2-level cluster states, are like 2-dimensional graphs. one-dimensional. Anyways, we perform proof of concept high-dimensional one-way quantum operations where the cluster states are transformed into orthogonal, maximally entangled, D-level, two-partite states by means of projection measurements. Our scalable approach is based on integrated photonic chips and optical fiber communication components, thus achieving new and deterministic functionalities. Okay, so there's a few things in here that I don't completely understand, like the definitions of D-level and four-partite and well, maximally entangled D-level two-partite states. I think I know what's going on there. Maximally entangled is like when you have an EPR pair, I'm thinking, but it's D-level. I don't know. We'll see. Cluster states are a particularly important class of multipartite. Okay, let's figure out what multipartite means, because that's going to annoy me. Having several or many parts or divisions. Okay, multipartite cluster state. A cluster state that has many divisions. I think it just means many divisions or something. Okay. Okay, that is those formed by more than two parties, such as multiple atoms, photons, and so on. Okay. So it says more than two photons. So multipartite state just means you have a state that has many photons in it, multiple photons, characterized by two unique properties. Maximal connectedness, that is, any two parties of the state can be projected into a maximally entangled state through measurements on the remaining parts. That I remember that from a previous paper. So you have your cluster state, and then you measure. I forget if it's the Z or the X quadrature or basis, whatever, but you can measure the other. Okay, as well as the highest persistency of entanglement. That is, cluster states require a maximum number of projection measurements to fully destroy entanglement in the system. Yeah, that's right. So there's some entangled states that are very not robust to measurement. So if I make a measurement on one of the if I make a measurement on one of the atoms or photons, then it could destroy the entanglement in all the entanglement in the state. However, these cluster states are have a high persistency of entanglement, meaning that for a cluster state, you can do a number of measurements before the all of the entanglement is lost. These properties make cluster states equivalent to universal one-way, also called measurement-based quantum computers, where different algorithms can be implemented by performing measurements on the individual parties of the cluster states. This approach greatly simplifies quantum processing, since measurement settings can be usually implemented more easily than the gate operations required in other approaches. Furthermore, cluster states have structural properties that protect the quantum information. That is, they enable topological quantum error correction. Cluster states have structural properties that protect the quantum information. That is, they enable topological quantum error correction. Okay, so this is something that I'm not familiar with. That's 11, reference 11. That is, they enable topological quantum error correction for minimizing computation errors. Due to the significant importance of cluster states, they have been studied in many different platforms. In particular, experimental realizations can be separated into two classes: discrete two-level, that is qubit, and continuous variable cluster states. Continuous variable systems are intrinsically high-dimensional, and they can be achieved using squeezed states. However, the quantum resource of these states relies on the level of squeezing, which is very sensitive to noise. 17. So reference 11 is something to do with topology and error correction. And 17 has something to do with noise. In contrast, discrete quantum states are less sensitive to noise than squeezed states. And even more importantly, their individual modes can be fully accessed and individually manipulated, making their use especially appealing. Nevertheless, increasing the number of particles to boost the computational resource comes at the price of significantly reduced coherence time and detection rates, and increased sensitivity to noise, restricting the realization of discrete cluster states to a record of 8 qubits. In a novel approach, the use of a discrete yet D-level, that is qdit, entangled state. Okay, what is a qdit? Okay, a qdit, the unit of quantum information described by superposition of D states. All right, simple enough. So instead of having a superposition of 0 and 1, so a qbit, then a qdit would be like a superposition of 0, 1, 2, 3, all the way up to whatever you want. Entangled states, yeah, so if we do these qdits, it has the potential to address several limitations of qubit cluster states. First, the quantum resource can be increased without changing the number of particles. Okay. Second, D-level quantum states enable the implementation of highly efficient computation protocols. And third, higher dimensions reduce the noise sensitivity of cluster states. The experimental realization of D-level multipartite cluster states is the key missing piece required to exploit these important benefits for high-dimensional quantum computation. Unfortunately, today's established quantum systems are ill-suited for increasing the dimensionality of discrete multipartite entangled states. For example, atomic and superconducting systems are mainly based on qubit schemes, and demonstrated high-dimensional photonic systems become experimentally complex and inefficient and typically suffer from degraded state purity when the number of photons used increases. The only D-level quantum states with more than 2 parties generated so far are 3-level, so that's like 3 basis states, 3 photon states in a bulk free space setup. Cluster states with 2 and 3 parties are locally equivalent to Bell and GHZ states, respectively. These are just other entangled states. While genuine discrete D-level cluster states require at least 4 parties. To date, these states have not been realized, nor have their entanglement properties and their tolerance to noise been investigated. Okay, here we present a general approach to prepare and coherently manipulate discrete D-level multipartite quantum systems based on the simultaneous entanglement, that is hyperentanglement, of 2 photons in time and frequency. By exploiting integrated photonic chips combined with fiber optics telecommunications components. Using this method, we present the first experimental realization and characterization of QDIT cluster states, as well as the first hyperentangled state employing only a single degree of freedom. Further, we use these states to perform proof of concept. Okay, this is a lot. But it's exciting, because that means that I'm going to learn something new. As a basis for the generation of D-level cluster states, we create hyperentangled states that support higher dimensions. Hyperentangled photon states usually employ simultaneously multiple different and independent degrees of freedom, which can be described as distinct parties of the state. These states can therefore be treated as multipartite, although the number of physical photons is not increased. Until now, such states have been realized only using combinations of fully independent degrees of freedom described by commuting operators such as polarization, optical paths, and temporal modes. Here we use intrinsically linked and non-commuting observables, 2 discrete forms of energy-time entanglement, namely time bin and frequency bin. Time bin entanglement refers to states where the photons are in a superposition of well-defined and distinct temporal modes, while frequency bin entangled states are characterized by discrete and non-overlapping frequency modes. Time bin entanglement can be generated by exciting a spontaneous parametric process in an optical nonlinear medium with multiple phase-locked pulses. On the other hand, frequency bin entanglement can be realized when the nonlinear medium is placed within an optical resonator where the emission bandwidth covers multiple resonances. Right, so here the pulses, the photons that are generated an optical pulse train composed of 3 pulses in this example excites a nonlinear medium where photons, signal and idler pairs, are simultaneously generated via a nonlinear spontaneous process, here four-way mixing, and a superposition of several time modes. Here d equals 3 given by the number of pulses, generating a d-level time bin entangled 2-photon state. Hang on a sec. Okay, so this pulse generates signal and idler pair and then this pulse generates this signal and idler pair. And these are entangled? The idler photons are entangled and the signal photons are entangled? Time bin entanglement can be generated by exciting a spontaneous parametric process in an optical nonlinear with multiple phase-locked pulses. Where the photons are in a superposition. Okay. Time bin encoding is a technique in quantum information science used to encode a qubit of information on a photon. pulse source of energy, time. A simple device of figure 1. All right. Superposition of several time modes. So I think somehow they're entangled. So I think this fuzziness means that they're supposed to be entangled in time. How are they entangled in time? Alright, this is gonna bother me now. Just wanna just give me a fast answer. Oh. Two spatially separated boxes of barometers through which is the signal in either the photons from SBDC or made to transmit individually. In quantum interference experiments, it is essential to ensure that the relevant quantum probability amplitudes are made indistinguishable. The scheme of Francis interferometry, post selecting the central peak. Theory. Beam pair of photons to either generated, directed to an unbalance, and the photons may take the long path L1 and L2 or the short path S1 and S2. I think I remember this. To ensure that there is no first order interference at the output. Okay, the photons are then detected at the photons are then detected at the single photon detectors D1 and D2. Difference of the photons' arrival times is recorded. It is well known that histograms exhibit three distinct peaks, and they come from the four probability amplitudes for joint detection of photon pair. So they both take the so photons 1 takes a short path, photon 2 takes a short path, they both take the long path, short, long, and long, short. The left and right peak is when they take different paths. And the central peak is when they both take the short or both take the long. which is why the central peak is twice as tall as the side peaks. Note that the separation between peaks is determined by optical path difference. There's no first order. We have thus obtained a time-band entangled state. Right. Right. That's what it is. This is why they're entangled, because we don't have path information. So if they both that's why, because, okay, so if this one takes the short path and this one takes the short path, then you're going to see a big peak when the time difference is 0. Or you're going to get a click here when the time difference is 0, because they're taking the same length path. But there's another possibility. They could both take the long path, in which case the time you'll get a big click. You'll get a click when the time difference is 0, because the path length is the same. So if they both take the short path, they both take the long path, it's the same distance that they're traveling. You'll get a click when the time delay is 0. And there's 2 possibilities. You get a big peak there. These peaks, the left and right peak, correspond to if one of them takes the short one and one of them takes the long one. And so this gap here, it's shifted to the left or to the right because the path lengths are different. So there's some time delay. However, this peak in the middle is 2 times the height of the peaks on either side, because there's 2 different ways to get to this peak, to get a click here. And so, but because we don't know which path, the short or the long, the photons took to get to the central peak. We don't know what path, so the state of the photon is in an entangled state, a maximally entangled state between the short and the long path. Right? We don't know which path the photon took to get to the center peak here. And if we don't have the path information, then we have entanglement. Okay. Well, I'm glad we solved that problem. So really, this is kind of misleading. Um, so the photons, so these signal and idlers are going to be now why in this case do you have time bin entanglement? Well, this photon here came from this pulse, and this photon also came from that pulse. These photons came from this pulse. These photons came from this pulse. Let's do time bin entanglement pulse string. Just explain it. All right, the basic idea is to use 2 consecutive laser pulses to pump a crystal with a nonlinearity. The time interval between the 2 pulses is t1, and the pulse duration is t2. The duration of the pulse is much smaller and fine than the separation. The coherence time of the laser pulse is much longer than the time interval t1, so that the phase between blah, 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 blah. When the 2 pulses pass through the nonlinear crystal, both have a certain probability to generate a photon pair via the process of parametric downconversion. If there is no other way except from the time difference to distinguish the 2 possible generations, the quantum state of the photon pair is given by this, where T1 and T2 represent the generating time of the photon pair. If there is no other way except for time difference to distinguish the 2 possible generations, So I think what it means is if I see this photon, right? So if I see this photon, the signal, and I see the idler, right? So then I say this photon, I say, okay, it could have been created from the first pulse. And the second photon, this photon is created from the first pulse. So I can only, if I can only measure differences in time, I don't know the exact time, right? I don't know the exact time that this photon pair were generated. That's what it is. I don't have time information. So this photon pair, so I take these four photons, these two pairs of photons, two pairs of photons, one, two. Which ones were generated first? And which ones were generated second? I don't know. All I know is I see two pairs of photons that but then but I could just say that, well, the ones that I detect, the pair that I detect initially at first, that comes from the first pulse, and the ones that I detect second come from the second pulse. Why would I ever think otherwise? Why would I ever? So these pulses are passing through a nonlinear medium, and then I'm detecting these pairs of photons with the time with delta t. Now, but can I say? But if I only have access to this delta t variable, so all I can do is measure whether I get a click on the photon detector and the delta t, the rate at which the clicks are coming. So the rate at which the clicks are coming will match the rate of the pulse string. However, I won't know if this pair came from the first pulse or the second pulse or the third pulse. So I don't have information on the time that these pairs are generated, and therefore they're entangled in time. So I can write down a maximally entangled state in terms of the time that these pairs are generated. But alternatively, if I send in a single pulse, well, now I know that all of these signal and idler photons were generated at the same time. And if I know they were generated at the same time, well, now I lose information about what their frequencies are, or the energy. And so now they're entangled in energy. And then if I just combine these two ways, these two entanglements, then I get this kind of graph where horizontally they're entangled in time and vertically they're entangled in frequency. It's time energy entanglement. Okay. That was a little bit painful, but I think we made it through. All right, so remarkably, if the time frequency product corresponding to the individual modes is well above the quantum limit, so we know that the delta t times delta e has to be greater than or equal to h bar over 2 or something. Frequency bin and time entanglement become independently controllable. Okay. So essentially, if the uncertainty in time and the uncertainty in energy are large, So if I make this pulse like if I make this pulse duration longer in time, that will increase my uncertainty in time, because now this pulse, some of the signal and idler photons will be generated at different times. They will all be generated at the same time, which will increase my uncertainty in time, and it'll decrease my uncertainty in frequency. And then also, if I increase this pulse duration, it'll decrease my uncertainty in time, increase my uncertainty in frequency. So kind of these, instead of having these cigar shapes or ellipsoidal shapes, they'll become more like circles, become less curved, less flat, less squeezed. They'll look more like this. Right, yeah, they'll look more like this. Right. C. An optical pulse training sets generating simultaneously time and frequency band entangled photon pairs. Right. Right, because if delta t becomes, if delta t goes to 0, then we're very uncertain in frequency. Right. Such hyper-entangled states can be produced by exciting the nonlinear element placed inside the resonator with a coherent set of multiple pulses, as long as the pulse separation is much larger than the photon lifetime in the resonator. In this case, the time bin component can be fully controlled in the temporal domain, while the frequency bin component can be completely and independently controlled in the frequency domain. That's pretty fucking cool. Yeah, so I'm guessing by changing the duration of the pump, you can affect the entanglement in time and frequency. When the duration is longer, the frequency is more narrow. How can the frequency bin be completely independently controlled? In our experimental implementation, we produced photon pairs using the nonlinear process of four-wave mixing with the microring resonator. By exciting the resonator with 3 phase-locked pulses and considering 3 frequency mode pairs, we generated photon states simultaneously entangled in time and frequency, described by the following expression. So, what is this one? Where the numbers indicate time bins, the letters indicate frequency bins. 2, 3. So there's 3 frequencies. And 3 time bins, so it's 3 pulses, and then 3 frequencies. They could, I guess those could be like, so these could be like the central frequencies of the pulse, maybe. No, just 3 different frequencies. Just 3 different frequencies for the signal and idler. Okay. The pulses probably all have the same pump frequency. And they're just in some tensor product state. Well, this is not entangled. It's just all the ways. So you can have, so this is just a graph. So you have that the signal and idler come from the first pulse, and they're both in the first frequency, or they're in the first both in the first pulse, both in the second frequency. So in their first pulse, first frequency. The signal is in the first pulse, the idler's in the first pulse, and they're both in the first frequency. They're both here. Okay. Respectively, the normalization though. This, how is it hyperentangled? Oh, I see. Okay, so it's a separable state in time and frequency, but in time it's hyperentangled, and in frequency it's hyperentangled. So that it's biseparable. Since any projection measurement performed in, for example, the time bin basis does not affect the frequency bin entangled substate, vice versa. In contrast, a cluster state is characterized by the fact that a projection measurement on one party affects the remaining portion of the state. An ideal compact 3-level cluster state, which is locally equivalent to a linear cluster in 1-dimensional lattice, as well as a box cluster 2-dimensional lattice. Whatever. Can be obtained by judiciously modifying the phase terms in equation 1. What does judiciously mean? Fairly? Carefully? Judiciously means with good judgment or sense. So just by carefully modifying the phase terms in equation 1, which then reads like this. All right, and then now with these phases, I'm guessing you have a cluster state, but that just means that it's probably no longer biseparable. Right. And this also probably satisfies some nullifier equations, which prove this is indeed a cluster state. To experimentally transform the hyperentangled state into this cluster state, access to the individual terms of the state is necessary while maintaining coherence. For multi-particle states, this is technically very challenging, requiring 2-party quantum gates, which are usually probabilistic. Since we are employing 2 different types of discrete energy time entanglement associated with different time scales, that is, time bin and frequency bin, it is possible to fully map the entangled state into the time domain to perform coherent state manipulations using synchronized electro-optic modulation. Figure 2. control phase gate gives access to the individual terms of the quantum state. This is like the temporally dispersing the individual frequency modes. Okay, so we take the frequency modes, disperse them time into different time slots via Bragg-Mir grading. That is because such that each, okay, so you convert frequency to time, such that each individual state term has its own time slot. See middle panel. An electro-optical modulator was used to change the phase of the individual state terms by alpha and beta over 2. And then there's some phase modulator. This is fucking amazing that they're able to do this. Wow. Wow. This is brilliant. Fucking brilliant. The phases of these ones are changed. Wow. The photons then enter the fiber Bragg grading array from the opposite end, such that the frequency to time mapping is coherently reversed. Oh my god, are you serious? By choosing these phases, the hyperentangled state is okay. The photons then enter the fiber Bragg grading array from the opposite end. So they go in here. They go through the Bragg mirrors. They go here. So this separates them in time. And then they're phase modulated. Wow, and then they do the reverse. Oh, they go through again? Hang on, they go in. They get shifted in time. Phase modulated. But then they go the opposite. Wow. So this is brilliant. Oh, that's brilliant. Wow. Okay, to confirm genuine multipartite entanglement, we determined an optimal entanglement witness for the cluster state. This witness detects the presence of a cluster state when its expectation value is negative. A minimum of -1 is reached by a theoretically optimal cluster state, that is, in the absence of imperfection or noise contributions. This witness can be reduced to a measurable witness containing 2 orthogonal measurements. Settings. confirming state exhibiting genuine. All right. Some condition that if it's -1, so yeah, it's close to -1. We then tested the impact of incoherent phase and amplitude noise in the measured state with respect to the expectation value of the witness via Monte Carlo simulations. Don't care about this stuff. This stuff is always boring. We also calculated the threshold. Found our dealer is highly robust towards incoherent noise. Oh. They can enter high amounts of amplitude phase noise. Most routers dealers seem to be more robust towards noise. Blah. To confirm the potential for quantum computation, we demonstrated that different and orthogonal entangled states can be generated by simply performing projection measurements on the parties of the cluster, which is the working principle of one-way quantum computers. We here show the shaping of the cluster states and transform them into different orthogonal. Hang on. We show the shaping of the cluster states and transform them into different orthogonal bipartite states. For this, we carried out two partite projections in either the frequency or time domain. Cluster state was projected on specific time and frequency modes, resulting in different orthogonal two-partite three-level entangled states in the frequency and time domains respectively. Quantum interference measurements were performed to confirm the presence of these two entanglements. A to C, the time-bin quantum interference measured by selecting two temporal modes, resulting in different phase shifts, the relative position and the maximum with respect to the zero phase, after projecting the cluster state on the frequency bins. So we projected onto AA, BB, and CC. B. How did they get those states? Oh, measure raw. Our work shows that integration is not, as is often regarded, simply limited to miniaturizing devices and reducing cost, but can in fact enable novel and powerful capabilities. Furthermore, our approach has an important scaling potential, as is advantageous compared to current methods based on two-level cluster states, since it can provide a better noise tolerance as well as significant improvement, are hampered by decreases in is therefore important to employ large cluster states with low photon number. 6, 8. A multi-photon cluster state approach, the detection rate diminishes more than the gain. Recently been shown that multi-photon states can carry hyperentanglement, which is these would enable quantum computation based on this system. The computation would be achieved in such a way that for receptor is achieved. Blah blah. Okay. Entanglement witness. I don't care about the witness thing. Well, actually, is mildly interesting. The presence of a genuine, pure, multi-part quantum state site, those states close to them can be identified measuring this particular entanglement witness operator. In general, cluster state is used to define set of eigenvalue equations. Eigenvalue equations. Right. I want to see how they do the projection. Okay. Quantum interference measurements shown in Figure 4 can be used to extract the amplitude of phase terms of the 4-part. The most generic wave function to express the 4 okay, this is just the hyperentangled state. Here we project onto time or frequency bin bases by means of temporal grading, optical filtering. The remaining 2 partite states were then measured in superpositions. Were then, for time band measurements, we employed 2-arm interferometer. The relative phase offset, I don't know. Really exciting. Alright, so I think those are the two areas of research that are exciting and I'm going to present on tomorrow. There's a few other papers here that I'm going to read probably tonight sometime. But yeah, I think these two things are very exciting. And thank you for listening.